Welcome to qnawire.
For part A, we're asked to find the wavelength, lambda, of a hydrogen atom going from the initial state of 4 to the final state of 2. The equation that governs this wavelength is 1 over lambda is equal to the Rydberg constant times 1 over n sub f squared minus 1 over n sub I squared. So in other words, lambda is just going to be the inversion of what's on the right side of the equation. So we're just going to raise both sides of the equation to the minus 1 to get lambda. So we have r sub h times 1 over final squared minus 1 over initial squared. And this all gets raised to the negative 1. So plugging in the values for the Rydberg constant, which is 1.097 times 10 to the minus 7, and the values for the final initial states of the orbital, we find that lambda is equal to 186 10 to the minus 9 meters, or 486 nanometers. You could write it either way, but I'm going to write it as nanometers. We can box that in as the solution for part A. Part B wants us to find the speed of the atom. The recoil speed is going to be equal to Planck's constant divided by the mass of the atom times the wavelength. And of course, wavelength, we're going to use units of meters, so it's 486 times 10 to the minus 9 meters. Planck's constant is 6.626 times 10 to the minus 34 joule seconds. And then m here is the mass of the hydrogen atom, so 1.67 times 10 to the minus 27. Plugging these values in, we find that the speed, v, is equal to 0.815 meters second. We can box that in as our solution for part B.